Hello and welcome to today's lesson looking at centripetal acceleration. In today's lesson, which forms part of the AQA A-Level Physics Further Mechanics topic, which is found on the paper 1 of the A-Level but not of the AS qualification, we're going to look at how to calculate centripetal forces in centripetal accelerations. So, in today's lesson, we're going to try and describe angular motion and the properties of an object moving in a circle, calculate centripetal acceleration in different applications, and calculate centripetal forces in different applications. So we're going to look at the following part of the AQA A-Level Physics specification. So we're going to look at the circular motion aspect of periodic motion, and we're going to focus on the bottom half of this particular specification point, focusing on centripetal acceleration and centripetal force. So in previous lessons, we've examined the circular motion of objects. So for an object to continue to move in a circle, a resultant force is needed that acts on an object towards the center of the circle. So we call that resultant force a centripetal force, and that can be a different force in different situations. So fundamentally, a centripetal force is a resultant force which acts towards the center of a circle, and it can actually be a combination of forces depending on the situation. You could also say that the centripetal force is a resultant force that acts perpendicular to the linear motion of the object. Okay, now, the centripetal force is a category that we can place different forces into. It's not a force itself. So an example of this includes a satellite orbiting the Earth. So here the centripetal force, which is the resultant force acting towards the center of the circle, or the force which acts perpendicular to the linear path of the object, is provided by the gravitational attraction between the Earth and the satellite. If we look at an example of a car going around a roundabout, well, the centripetal force in this example is the friction between the car and the road. If we look at the idea of a ball on a string being swung around in a circle, the centripetal force is the tension in the string. Now, we can calculate the resultant force in a situation by calculating the resultant center-secant force in that application. So to calculate the centripetal force, you've got to work out the overall force acting towards the center of the circle. So to do this, you've only got to consider forces which act towards the center of the circle. So this overall force can be equated by the general centripetal force equation to work out values. Now just remember, a force which doesn't act towards the center of the circle, i.e. parallel to the linear path, it does not need to be considered. So, we know that a centripetal force must be a resultant force because the object is accelerating. Now, the only thing that can cause an acceleration is a resultant force. Now, we know this as there's a tangential direction of an object, and this tangential direction is constantly changing in the motion, so therefore the velocity of the object is constantly changing, so therefore the object is accelerating. And since F equals ma, which is Newton's second law of motion, the object must accelerate in the same direction as the resultant force. Now remember, circular motion is just an application of Newton's laws of motion. So Newton's laws, such as the first law, the second law, and the third law, they all still work in circular motion. Now, as this object is accelerating, there must be a resultant force acting towards the center of the rotation. Okay, now this means that there must be an acceleration in the same direction as the resultant force which causes this. It's Newton's second or Newton's first law of motion. So therefore, there must be an acceleration acting towards the center of the circle when an object moves in a circular path. Now, the acceleration is always produced in the same direction as the resultant force which causes it. So as it goes along around the circle, the centripetal acceleration and the centripetal force always acts towards the center of the rotation. So the acceleration produced by the centripetal force is called the centripetal acceleration, and it always acts from the body to the center of the circle. Now remember, it's the center of the circle which is the center of mass of the system, not the surface an object is on. So for example, humans on the surface of Earth experience a centripetal acceleration towards the center of the Earth, not the surface of the Earth, the center of the Earth, because that is where the center of mass of the system will be. Now, in this particular example, is provided by the gravitational attraction between the human and the Earth. Now, as we know from previous lessons, this is going to be 9.81 meters per second squared. Now, in fact, there's a further centripetal acceleration produced by the fact that the Earth is spinning, which actually has a centripetal acceleration of about 0.034 meters per second squared, which is significantly smaller than the acceleration produced by the gravitational attraction between the human and the Earth, which does mean that if the world did stop spinning suddenly, you'd still be attracted to the centre of the Earth and you wouldn't float off into space like some people seem to think that you would be. Now, the centripetal of an object can be derived, the centripetal acceleration of an object, can be derived if we look at the segment of a path taken by an object moving in a circle. Now, just to clarify this, according to the specification, you do not need to memorize this derivation of the centripetal acceleration, but it's always useful to see where these terms derive from. So, if we consider the change in velocity of an object is linear velocity, which is moving angle subtended from the center of the circle, we can call this change in linear velocity delta v, and the change in angular displacement delta theta. So in a time of t, the object changes velocity by delta v and changes angle by delta theta. So in a certain time, the linear velocity and the angular displacement will change. So we can consider the following section from the circle of rotation. Now we consider this segment of the circular path to be very, very, very small. So delta theta can be considered very, 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 very small because the path that it's projecting out is very, very, very small. Now, we can use trigonometry to state that, well, sine is equal to opposite over hypotenuse. Now, if we look at this particular right-angled triangle, the opposite is delta v and the hypotenuse is v, so therefore sine delta theta equals delta v over v. Now, because this is a very, very, very small angle, we can use something called the small angle approximation, which you may have come across if you do A-level mathematics. Now, basically, all you've got to know for A-level physics is that for very small angles, sine theta will equal theta. So in this particular example, sine delta theta just becomes theta. Now you might ask, well, what's the cutoff with a small angle approximation? Well, it only tends to work for angles of 10 degrees or less. So now we can say that sine theta delta theta equals delta v over v. So delta theta equals delta v over v. So we rearrange that to make delta v the subject. So it's v delta theta. Now, as we know that acceleration from GCSE physics is A equals delta v over delta t, and we're assuming, by the way, that there's constant acceleration provided by a constant resultant force, we can rewrite this because we know what delta v is now. We know that delta v is v delta theta, so now A equals v delta theta over delta t. So A equals v delta theta over delta t. We know that delta theta, change in angular displacement, over delta t, change in time, is just angular velocity. So therefore, centripetal acceleration equals v at times by the angular velocity, or a times by omega. A equals v times omega, and that's the equation used to calculate the centripetal acceleration. Now we can then substitute v equals r omega into this equation to get three different equations for centripetal acceleration. So we can say that a equals v omega, a equals r omega squared, or a equals v squared over r. Now centripetal acceleration is just an example of an acceleration, so it's given the same units as linear acceleration, meters per second squared, or ms minus 2. Now you're given at least one form of this equation in your equation book. Now each equation can be used in any situation regarding circular motion. So you've got to choose the equation which has the suitable information given to you in the puzzle. So if you were given v and r in the question, you'd use the equation on the right. If you were given v and omega, you'd use the equation on the left. And if you were given r and omega in the question, you'd use the central equation. Now, I would memorize the units of each quantity. Now, the centripetal acceleration value will always act towards the center of the circle of rotation. So you've got your direction straight away there for your acceleration value. So let's have a look at the question on this. So in the spirit of physics, we throw Sam into space. He goes into orbit around the Earth 70 kilometers above the surface, and he orbits once every 1,860 seconds. So we can calculate the centripetal acceleration Sam feels towards the center of rotation. Now remember, the radius is always measured as the separation between the centers of masses of the different objects. So this means we're not measuring from the center of the surface of the Earth, rather we're measuring from the center of the Earth. So let's look at how we answer this question. So we've got to work out angular velocity first. That's the change in angle over time. And we know that in one full circle, 2 pi, we know that the time is 1,800 seconds. So you get an angular velocity of 0.0035 radians per second. You then pop that into the equation A equals r omega squared. Now a few things. Firstly, we are measuring from the center of the Earth, because we're measuring from the center of the rotation. So we've got to add the actual size of the Earth to the distance from the surface of the Earth that Sam is. So we're doing 6,400 plus 70. Then you've got to convert your kilometers into meters, and you get an answer of 78.8 or 79 meters per second squared, when we give the appropriate number of significant figures and we give the correct units. Now remember, we know that 1g, which is the acceleration due to gravity on the Earth, is 9.81, so 79 meters per second squared is about 8g. Now, physicists think we can use this concept in the future to produce acceleration due to gravity in space, because if we rotate an object in space fast enough, there'll be a centripetal acceleration of the same size as the acceleration due to gravity on Earth, 9.81, which could possibly produce an artificial gravity on a space station. So producing a centripetal acceleration at the same size as acceleration due to gravity is a current way of thinking of how we can create gravity on a spacecraft, or we can simulate that effect. Because if we can actually produce a centripetal acceleration of 9.81 meters per second squared, it will actually replicate the conditions that we experience on the surface of the Earth. So the rotation of an object will produce a constant acceleration towards the center of the spaceship, mimicking the effect of gravity. Now, we know our equations for centripetal acceleration, which we just talked about before. Now, we can use these three equations to derive the equation for centripetal force, because we know that F equals ma, and we know all of these equations give us a value for a, so if we times all of these particular terms by m, we will get our centripetal force. Now, once again, this can happen because circular motion is just an application of Newton's mechanics, so Newton's laws of motion still have to be obeyed. So now, if we just add an n term in front of all those equations, we can get an equation for centripetal force. So the centripetal force, which always acts towards the center of the rotation of an object, it is always a resultant force, it's always measured in newtons, can be given by F equals mv omega, F equals r omega squared, or F equals mv squared over r, with the bottom term being probably the most commonly known equation for centripetal force. Now, you're given at least one form of this equation in your equation book, but I would memorize the units of each quantity. Now, like for acceleration, each equation can be used in any situation, but you've got to choose the one with the most suitable information given in the puzzle. Now, again, always remember that this equation calculates the resultant force acting towards the center of the circle. Now, from looking at these three equations, you can see the factors that affect the resultant centripetal force. M, the mass of the object moving. V, the linear velocity at which the object moves. And R, the distance from the center of the circle of rotation. You'll also say to me, well, what about omega? What about angular velocity? Well, we know that omega is equal to r, so we can say that linear velocity v equals r omega, so therefore omega equals v over r, so it comprises both linear velocity and the distance from the center in this particular factor. Now, when considering a situation, only these factors can affect the centripetal force. All other factors do not affect the size of centripetal force produced, and we know this. The evidence for this is it is not found in the equation. If a term is not found in an equation for a factor, it can't influence it. So, because any term not in the equation will not be relevant to the situation present. Now, the centripetal force must always be acting as the resultant force in circular motion. It must always act towards the center of the circle. Now, we know it's there because the object is constantly changing its tangential direction. There must be a resultant force causing this acceleration. The resultant force must be acting towards the center of circular rotation. Now, if that force was removed, the object would move off at a tangent with a linear velocity. Now, we can actually calculate this value for centripetal force because from our previous equations, we can work it out. But we can also now equate this term that we've just calculated to other forces found in a situation, because we know that the centripetal force is the resultant force towards the center of the rotation. So as well as saying that F equals mv squared over r, or F equals mv omega, or F equals mr omega squared, we can also say F equals r minus t, because that's the resultant force towards the center of the circle in this situation. So we can equate the two terms to each other. Now, you've got to be able to do this for a variety of different situations. So, for example, let's look at this particular situation. We know that F equals mv squared over r, just to take one of the equations for our particular example. But we also know that from this particular situation, you can see in front of you, mg is also the centripetal force, because mg is the resultant force acting towards the center of the circle in the situation. So we can actually equate the two. We can say mv squared over r equals mg. We can cancel those m terms on either side of the equation, and we can now say that v squared over r equals g. And now this process works for all forces that act as centripetal forces. So regardless of the question that you're given in an examination, if you equate your general equation to the equations which are shown to you in the example, you can work out and derive a value in a situation. So for all situations, you've got to determine the resultant force, equate it to a centripetal force equation, and then rearrange it into the appropriate format. So let's have a look at a particular situation and look at an example question. So if we go back to Sam orbiting in space, we can now work out the centripetal force on him. So what we do now is we got our value for omega from the previous question. We've got our value from A in the previous question. So we can work out what F is because we know F equals ma. So we've now got our value for acceleration, which is 79. We multiply it by our mass, which is 70. So we get an answer of 5,500 newtons, which we know to the correct number of significant figures. We'll put a unit on there, and we know that it must be acting towards the center of the circle. Now, the resultant force, the centripetal force, as well as acting towards the center of the circle, we also defined that it must be acting perpendicular to the linear motion of the object. Now again, we're carrying out now an application of Newton's laws. Now this means that if it is acting perpendicular to linear motion, that the centripetal force cannot affect the linear velocity of the object. Now this is actually proven by considering the laws of energy conservation, because we know that work done equals force times by displacement in the direction of the force. Now you'll notice in this particular situation, the object is not displaced at all in the direction of the centripetal force. It's in fact moving perpendicular to the direction of the force. So if we now said work done equals force times by displacement, displacement equals 0 because it's traveling in a different direction, so the work done is equal to 0. So basically, no work is done by the centripetal force on the object because there's no displacement in the direction of the force. So as no work is done, no energy is transferred, so the kinetic energy store of the object remains constant, so therefore your orbital speed, your linear velocity, will stay the same. Now the orbital path is what we call a line of equipotential. This is a line where the energy store of an object doesn't change as it moves along this line. Equi equal the same, potential energy. A line where energy stays equal, stays the same. So, if an object moves along a line of equipotential, by definition, no work can be done. Now, this is a reason as to why objects such as a moon, such as a satellite, can achieve a stable orbit in the universe and not deviate from that particular orbit. So, for example, the moon, no more energy is required to maintain the moon's orbit around the Earth. Now, for a fields aspect, such as gravitational fields, electrical fields, magnetic fields, we state that the orbit is in the line of equipotential. There is no work done when that particular object is moving along its orbital path. So, if we have learned in today's lesson, we know what centripetal acceleration is and how to calculate centripetal acceleration, and we know what the centripetal force is and how to calculate the centripetal force. So if you've learned in today's lesson, you can describe the angular motion and the properties of an object moving in a circle, you can calculate centripetal acceleration in different situations, and calculate the centripetal force in different situations. I hope you've enjoyed today's lesson on centripetal forces and centripetal acceleration. In the next lesson in this course, we will look at applications of centripetal forces in more complicated situations. Thank you very, very much, and I hope you've enjoyed today's lesson. Have a lovely day.